Hi everyone, welcome again to Demystify Maths. Let's continue with part 2 of real numbers. If you haven't checked out part 1, the link is in the description box. Today we will cover 1.3 as well as 1.4. So go grab your registers. And yes, have you hit the subscribe button? Press the bell icon as well. So the next concept in this chapter is about the type of numbers. There is a separate video which explains the entire number system in detail. The link is in the description. But just a quick recap here. Rational numbers are the numbers which can be written as P by Q form. That is integer by integer form. And denominator cannot be 0. So your natural numbers and your whole numbers and the integers, all of them come under the heading of rational numbers. And obviously the numbers which are not rational numbers are irrational numbers. Now how do we recognize them? Now we have fractions and decimals. So fractions and decimals, they can be converted to each other. So when we convert any fraction into a decimal, there are three possibilities. First, when you convert a fraction into decimal, you get a terminating decimal expansion. That is, when you divide, after some time, your division is completed. Such fractions are called rational numbers. They belong to the category of rational numbers. Then the second is, when you divide, when you convert that fraction into decimal, it is non-terminating but repeating. Right? There is a pattern, there is a number which will continuously repeat itself. Like when you divide 10 by 3, you get 3.3333 continued and you write it as 3.3 bar. Such numbers, such fractions or decimals, they are also termed as rational. But the third type, where it is non-terminating and not repeating, where suppose 22 by 7, if you divide it, there will neither the division will end nor there will be a pattern to it. Such numbers are irrational. Exercise 1.3, prove that root 5 is irrational. This question can come as prove root 2 is irrational, root 3 is irrational, or root 7. So how do we begin with these questions? We begin with an assumption that let root 5 is rational. And by the very definition of rational number means integer upon integer form. Any number which can be presented as integer upon integer form where denominator is not 0. So that means I can say that root 5 is equals to a by b, where a and b are co-prime. This is very important. Even if there were some other two numbers, we have cancelled the common factors and then we have reached a by b are co-prime. This is very important because this is what we will prove as contradiction. So root 5 is a by b, where a and b are co-prime. That means there is no factor between a and b. Now let's cross multiply. I will get root 5 into b is equals to a. Now to get rid of the under root there, I will do squaring both sides. And when I square both sides, I will get 5b square is equals to a square. Now it is clearly seen here that 5 multiplied by something gives you a square, right? This means 5 divides a square, because 5 multiplied by b square is giving you a square, which further implies 5 divides a. If 5 divides a, this means 5 multiplied by some other number, let's suppose c, is equals to a. Right? Now, I'll put this value back from where we started. I'll put this value back here. So what will I get? 5b square, and instead of a, now I will write 5 c whole square, complete a square, right? And after that I will get 5b square is equals to 25c square, right? And 5 and 5, so I get b square is equals to 5c square. Now 5 multiplied by c square is giving you b square. This implies 5 divides b square, which further implies 5 divides b. Now here, if you pay attention, we have already proved 5 divides a, and now we have reached that 5 divides b. So this is 1 and this is 2, right? So from 1 and 2, 5 divides both a and b, which even tells that a and b are not co-prime. Therefore, our assumption was wrong and root 5 cannot be rational. Hence, root 5 is irrational. This is the same method you will apply for root 3, root 5, root 7, but not for root 9. Root 9 is not irrational because root 9 is equals to 3 and 3 is very much rational. Question 2, prove that 3 plus 2 root 5 is irrational. So we begin with the same assumption that let 3 plus 2 root 5 is rational. And if I declare it rational, it can be represented as integer upon integer form, that is a by b. Now if I cross multiply, I get 3b plus 2 root 5 into b is equals to a. Now keeping 2 root 5b on one side, a minus 3b, or I can say root 5 is equals to a minus 3b upon 2b. Now both of them are equal. Now a and b were integers. That means a minus 3b upon 2b is rational because a and b are integers, which implies that root 5 is also rational because both of them are equal, right? But which is not true. But root 5 we just proved, but root 5 is irrational. How can a rational number be equal to an irrational number? This implies that our assumption was wrong. And the given question, that is 3 plus 2 root 5, is actually irrational and not rational. Next question. Question number 3, again, that we have to prove the following as irrational. Now first part is 1 by root 2. We begin in the same manner that let 1 by root 2 is rational and that is y equals to a by b. If I cross multiply, I get b is equals to root 2a or root 2 is equals to b by a. Now b by a is rational, right? Which implies that root 2 is rational. But we already know that root 2 is irrational, right? Which implies that 1 by root 2 is also irrational as our assumption was incorrect, right? Second one is 7 root 5. So again, let 7 root 5 be equals to a by b. Root 5 will be equals to a by 7b. Again, a by 7b is rational, which implies root 5 is rational. But we know that root 5 is irrational. That means our assumption was incorrect and 7 root 5 is irrational. This also proves that a product of a rational number and an irrational number is irrational. Then the last one, 6 plus root 2, again, let 6 plus root 2 is equals to a by b. I will cross multiply 6b plus root 2b is equals to a. Root 2b is equals to a minus 6b, and root 2 is a minus 6b upon b. Now this here completely is all about integers. So a minus 6b by b is rational, which we have proven equal to root 2, which implies root 2 is rational. It should be rational because both of them are there is an equality sign between them. But we already know that root 2 is irrational. That means our assumption was wrong and 6 plus root 2 is irrational. This also makes us conclude that a sum of rational and irrational number is also irrational. Now exercise 1.4, where actually without performing the long division, we have to state whether the given rational numbers have a terminating decimal expansion or a non-terminating decimal expansion. Now what is the criteria or method used to recognize it? First, we will find the factors of the denominator, right? That is from where the numerator will be divided by the denominator. Now, denominator should have factors 2 or 5 only. Means there can be all 2's, there can be all 5's, there can be some 2's and some 5's, but not any other number other than 2 and 5. This only means only 2 or 5. If there is 2, 5 and a 3, there is 2, 5 or a 7, then it will not have a terminal decimal expansion. But if it is only 2 and 5, it will terminate. So let's look at the first part, which is 13 upon 3125. So we will find the factors of 3125. So if we find the factors of 3125, let's start dividing by 5. 5 6 are, 2's are, 5's are, 625, 5 125's are, and then 5 25's are, and then 5 5. So denominator here can be expressed as 5 to the power 5, right? And there is no other factor than 5. 2 was acceptable, other than 2 nothing is acceptable. Hence this one will have a terminating decimal expansion. Let's do the next part. The next part is 17 by 8. 17 by 8. So we already know 8 is nothing but 2 cube. All 2's, nothing other than 2. So even this one will have a terminal decimal expansion. Then next we have 64 by 455. So now 455 needs to be prime factorized. So if I take the prime factorization of 455, it is 591s, and then it is 7. Now we've got something else. So this will be 7 13s. So there is a 7 also, there is a 13 also. So here it is actually 64, 5 into 7 into 13. The moment you have factors other than 2 or 5, it will have non-terminating decimal expansion. It should be only 2, only 5, or 2 or 5. Both of them can be there, but no other factor other than 2 or 5. Fourth part, 15 upon 1600. So 1600 we know is 16 into 100. And I can write it as 16 into 25 into 4, or if I prime factorize it, it is 2 raised to power 6, 5 raised to power 2. Now only factors of 2 and 5, therefore this one will be a terminating decimal expansion. Then 29 by 343, we know 343 is 7 cube. So it will be non-terminating repeating decimal expansion. Non-terminating repeating. Then the next part is sixth part. It is already given in factors 23 by 2 cube into 5 square. We can see only 2's and only 5's. So therefore this will be a terminating decimal expansion. Then seventh part, let's look at the denominator straight away. 2 square 5 7 7 raised to power 5. Now 2 and 5 are okay with us, but if there is anything other than 2 and 5, then it is non-terminating repeating decimal expansion. Only factors of 2, only factors of 5, or both of them. No other number. Now, eighth part, 6 by 15. But you can see that you can reduce it further. If I reduce it by 3, I will get 2 by 5. If you do not reduce it, then you will say 15 has a factor 5 and 3, right? But then you have to make sure that the given one is in the reduced form. 2 by 5, denominator only has 5. That means this one has a terminating decimal expansion. Then 35 by 50, I can again see that I can reduce it further. I'll reduce it by 5, I'll get 7 by 10. Again, denominator has only 5 and 2. So this one is also terminating decimal expansion. The last one, again I can see I can divide by 7, I'll get 11 by 30. So it is 11, 3 into 2 into 5. 2 and 5 are okay, but 3 we don't want it there. So this one will be a non-terminating decimal expansion. So in the denominator, we need only 2 or 5. Question number 2, write down the decimal expansions of those rational numbers in question 1 which have terminal decimal expansion. So we just proved the first part, which was 13 upon 3125, and we could write it as 13 upon 5 raised to power 5. It had terminal decimal expansion. Now, how do we convert it into decimals? Of course, you can divide 13 by 3125, but we prefer making tens in the denominator. So we have multiplied numerator and denominator both by 2 raised to power 5. Why? So that I get 10 raised to power 5 in the denominator. So it is just 13 into 32 left to multiply, which is 416 upon 10 raised to power 5. Now the decimal shifting is easier. You just have to shift 5 decimal places. So it is 0.00416 is your answer. Easier rather than dividing 13 by 3125 the longer way. Then the second part also, 17 by 8, we also proved it to be terminal decimal expansion. This one is even simpler. You can straight away also divide it as 8 2s are 16, and then 8 1s are, then 2s are and 5s are. So you can write it straight away also. This is still simpler. After that, fourth part was 15 by 1600, where 1600, if prime factorized in terms of 2's and 5's, we got 2 raised to power 6 and 5 raised to the power 2. So we want even the power of 5 also as to be 6. So 2 raised to power 6, 5 raised to power 2. I will write 4 more powers and multiply by 4 more powers, right? So in the denominator, now I have 10 raised to the power 6. Now only numerator multiplication is left. If I multiply it, I'll get 9375, and that is 625 multiplied by 15. Now shift of decimals to 6 places, it will be 0.009375. Then sixth part was proved to be having terminal decimal expansion, which was 23 upon 2 raised to power 3 into 5 raised to the power 2. So I can see I only want one more 5 here. So 23, 2 raised to power 3, 5 raised to power 2. I'll multiply by 5, numerator and denominator, so that this becomes 5 cube only, and it will be 23 into 5 upon 2 cube 5 cube. And if I simplify the numerator along, I will get 115 upon 10 cube. So just shift off 3 places of decimals, or if you want me, I can write it as 1, 2, 3, and 0.115 is your answer. Then we had 8th part also, which was proven, which was 6 by 15. You can straight away also divide it, which is equals to 0.4. And then 9th part, which was 35 by 50, needs to be converted. Even this can be easily done. If you reduce it, it is 5 sevens and 10, and your answer is 0.6. Last question, question 3. Now the following real numbers have decimal expansions as given. We have to tell whether it is rational or not, and we even have to say something about the prime factors of the denominator or the q. Now first one, if we see here, the decimal expansion is ending at 9. So is it rational? Yes, it is very much rational. And because the termination is occurring, we can say that if this is expressed as P by Q form, Q will have factors of 2 and 5 only. That is what we have to conclude. Then the second part. Now this, if you see here, these dots tell us that it is not ending, it is not terminating, and neither it is repeating. So this case is an irrational number, right? Non-terminating but repeating are rational, but not terminating, not repeating are irrational. Like the last one here, it is not terminating, but then it is repeating types. Even the repeating types is a rational number. And yes, the denominator is very much possible here. What is the denominator? Can you guess? It is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the denominator here is actually 1, 2, 3, 4, 5, 6, 7, 8, and 9. This finishes your chapter. There is another video with advanced questions on this chapter. The link is in the description box. If you like it, please share it, subscribe it, and press the bell icon right now.